main goal in chem activity number 5 is to review intermolecular forces. Intermolecular forces, that is the forces between molecules, very important in organic chemistry for understanding a variety of properties, including boiling points and melting points, and even considering acid-base properties, etc. Now, intermolecular force is mainly a concept that was introduced in first-year chemistry, and therefore it will be a review in this chem activity. But first of all, we need to make a detour and review the properties of polarity in bonds and in molecules. So to start off, I have a representation of hydrogen fluoride, a very simple molecule, and it's a great molecule to examine the idea of bond polarity. Now, when we're dealing with a compound that it has covalent bonds, the reason why we would have a polar bond is because there's an unequal distribution of electron density. The reason why there would be an unequal distribution of electron density is because the hydrogen atom and the fluorine atom have different electronegativities. In other words, they have different attractions for a shared pair of electrons. If hydrogen and fluorine had the same attraction for the shared pair of electrons, then we would have an equal distribution of electron density throughout the molecule, and there'd be no degree of polarity. Now, you can think of polarity as, in a sense, being a separation of charge density. That is, there'll be a positive side and a negative side. Now, as I say, we can predict the fact that hydrogen-fluorine bond is polar by knowing that fluorine is much more electronegative than hydrogen. Now, some of the ways that we've represented this in the past is we would say, for instance, that fluorine is delta negative and hydrogen is delta positive. This indicates a partial negative charge, a partial positive charge. This is different than saying these are cations or anions. It's saying there's an unequal sharing of the pair of electrons between the hydrogen and fluorine. Fluorine's pulling the electron density more towards it, leaving the hydrogen somewhat delta positive, the fluorine partially negative. Another way that we represent this is we draw a bond dipole arrow. Now we point the arrow in the direction of the atom that is more delta negative. One of the ways that I remember that is when we draw the arrow in this fashion, on the left-hand side, it kind of looks like there's a positive inherent in that arrow. So that's on the positive side. The arrow is pointing towards the more negative side. Now, when you have a very simple molecule like this, that is a diatomic molecule, in a sense, the bond dipole represents the molecular dipole. That is, the entire molecule has some degree of polarity. Now, before we go on, I just would like to remind you about something in terms of knowing which atom is more electronegative than another. Now, certainly one can think about the trend in the periodic table where moving from left to right and bottom to top, we have an increase in electronegativity. So the upper right-hand corner involve the most electronegative elements. Last year in my class, I introduced a little mnemonic that hopefully would help students remember the relative electronegativities. Sometimes the trend in the periodic table is a little hard to interpret. So here's the mnemonic. It went something like funny, which of course represents fluorine, old clown, never, breaks, into, silly, comical, hiccups. Now, if you can think of another way of representing this, great. But you might want to commit to memory this relative order, because these are the elements that are involved in organic chemistry, and these are the ones that you're going to need to use in making these kinds of comparisons. So once again, funny, old clown, never, break, into, silly, comical, hiccups. So therefore, of course, fluorine is more electronegative than hydrogen. Now, we will also be using boron and silicon sometimes, and we'll need to make a comparison in that case, but these are the most common elements. Okay, so this is on the basis of knowing electronegativity. We can also look at bond dipoles, and therefore, for simple molecules, molecular dipoles, by measuring the dipole moment. Now, the dipole moment can be measured by using a device that sets up an electric field. And so, for instance, if we put hydrogen fluoride between two plates, and if the electric field is not on, we would expect the hydrogen fluoride molecule to, in a sense, be moving around randomly, oriented in a variety of different directions. And so you can see that the fluorine is represented by the purple, the gray is the hydrogen, and the molecule is oriented in a random way. If we then turn on the electric field so that one of the plates is positive and one of the plates is negative, the molecule will align itself such that the more delta negative will be oriented towards the positive plate. In other words, the fluorine will be oriented towards the positive plate, and the delta positive will be oriented towards the negative plate. In a sense, what this does is it's a measure of the degree to which the plates can hold a charge, or in other words, the capacitance. So if a molecule is relatively polar, and in this case if the bond is polar, then the capacitance of these plates will increase. Now, if the molecule is not polar, the capacitance doesn't increase, and we'd say that the dipole moment is 0. Now, dipole moments are measured in units of Debye, and this is after a famous Nobel laureate chemist, Peter Debye. So we'll honor his last name for referring to the molecular polarity. So you can see that hydrogen, H2, 0 dipole moment, HF, dipole moment of 1.7. Okay. Now, the actual value of the dipole moment is not necessarily so useful. But what is useful is making a comparison between different molecules. Okay, so in the case of hydrogen fluoride, of course, the bond dipole corresponds directly to the molecular dipole. But if we want to look at molecular dipoles for more complex molecules, we need to consider both the bond dipoles and the molecular geometry. So I have a series of molecules here, and what we're going to do is consider their geometries, the differences in electronegativity in the chemical bonds, and in a sense try to predict whether or not we'd expect the molecule to have a dipole moment or a molecular dipole. I'll do a couple of examples with you, and then I'm going to ask you to turn the video off for a moment and try some other examples yourself, and then we'll compare answers. And then I'll make some comments about being careful in terms of actually paying attention to the dipole moment values. Okay, so let's start first of all with methane, which is on the left-hand side. And one of the general rules of thumb is, for the most part, even though there is a difference in electronegativity between carbon and hydrogen, that difference is small. And so for the most part, it's perhaps best to consider that that bond is relatively non-polar. There'll be times later on in the course where we will actually pay attention to that difference. But if you have a series of carbon-hydrogen, carbon-hydrogen, carbon-hydrogen bonds, consider them to be essentially non-polar. Therefore, for methane, the fact that it has a 0 dipole moment and there's no possibility of drawing a molecular dipole for that molecule, this molecule is essentially non-polar. If we consider, however, the chloromethane, which is the next molecule on the right, we know that the carbon-chlorine bond is indeed polar, where chlorine, being more electronegative than carbon, we would say that the chlorine is delta negative and the carbon is delta positive. And I'm going to draw a bond dipole in the direction of the chlorine. I'm going to consider that the hydrogen-carbon bonds are essentially nonpolar, Therefore, this entire molecule will have a molecular dipole. So what I've just drawn here is, in a sense, the bond dipole, and then I'm going to draw an entire molecular dipole, which in a sense is saying that the whole molecule is polar. If you put this molecule between charged plates, you can measure a dipole moment of 1.94 dBi. Okay, so in the exact same way, we can consider this molecule right here, which is the bromomethane. It has a bond dipole, and we can also draw a molecular dipole, considering the three-dimensionality of, or the molecular geometry of that molecule. And as you can see, it has a dipole moment of 1.79. And then lastly, we have here the iodomethane, and indeed this would be a bond dipole. And then of course we have the molecular dipole in the direction of the iodine. Now, as you might expect, the chloromethane would in fact be more polar than the iodomethane. This is because the difference in electronegativity between carbon and chlorine is greater than the difference between carbon and iodine. Now, you can consider that by looking at the periodic table, but also if you look at our mnemonic here. If you consider the carbon and then think about chlorine, chlorine is further away from the carbon. Chlorine is more electronegative than the carbon. That's a more polar bond. Bromine is closer to the carbon. The difference in electronegativity between bromine and carbon is smaller. That's a less polar bond, and etc. Okay? So in this case, the dipole moments, I should say the molecular dipole moments, match perfectly with what we would expect based on differences in electronegativity. Indeed, the chloromethane is a more polar molecule than iodomethane. All right, so I'm going to stop for a minute and ask you, in a sense, to complete key question number 1. So you're going to complete the rest of the diagram by indicating bond dipoles and molecular dipoles. Okay, so you've had a chance to look for the bond dipoles. And the idea is that once you look for the bond dipoles, you then consider the geometry and then decide whether or not the entire molecule is polar. As not mentioned in the past discussion, but perhaps you remember from last year, these bond dipoles you can think of as being vectors. And so, in a sense, the vectors can be added, and if you have a net vector in one direction, well, then the entire molecule will be polar. Okay, so considering this tetrachloromethane, I know that I have a bond dipole in each of these different directions moving away from the carbon and towards the chlorine. Now, because the tetrachloromethane is perfectly symmetrical, I would expect that all of these bond dipoles will cancel. And therefore, not surprising, this molecule is not polar. It has a zero dipole moment. So this molecule is non-polar. And I don't draw a molecular dipole arrow at all because all the bond dipoles cancel. Now, sometimes students have trouble looking at a molecule that's supposed to be represented in 3 dimensions and to decide, well, do the bond dipoles cancel? One of the things to consider is if the molecule is perfectly symmetrical, as is the tetrahedral structure, then you can be certain that the bond dipoles will cancel. Just as a bit of a comparison, let us say that these were chlorines, and then I'm drawing the tetrahedral structure, but I put fluorines here. Now this molecule is not symmetrical, and therefore I would expect that indeed there are bond dipoles, but the bond dipoles do not cancel. Because the fluorines are more electronegative than the chlorines, I would anticipate a molecular dipole in the direction of the fluorines. Similarly, we see the example of this 1,1-dichloroethane, where we've got bond dipoles in this direction, bond dipoles in this direction. I'm not going to worry about the hydrogen-carbon bond. I'm not going to worry about the carbon-carbon bonds. And overall, I would expect a molecular dipole in the direction of the two chlorines. And the dipole moment, the molecular dipole moment, in a sense, confirms this. Now, of course, water is definitely a polar molecule. And based on its bent molecular geometry, and based on the fact that we've got bond dipoles in the direction of hydrogen to oxygen, overall there would be a molecular dipole in the direction of the oxygen. And then finally, in the case of acetone, I'm not going to worry about the carbon-carbon bond, but rather the carbon-oxygen bond. And definitely we have a bond dipole in the direction of the oxygen, and overall a molecular dipole. And indeed, the dipole moment confirms that this molecule is polar. Okay, so that's how we would represent it, in a sense, based on knowing about the differences in electronegativity and focusing on the more polar region. Now, in a sense, you can shortcut by remembering that carbon-carbon bonds are definitely not polar. Carbon-hydrogen bonds are generally not very polar, and you can essentially ignore them. And therefore, you're looking for that part of the molecule where you have differences in atoms that are present, different from carbon and hydrogen. So those various functional groups, or having a halogen present. And you know that that region has the potential to be polar. As a last comment, in the first row, you can see that the dipole moments seem to match the differences in electronegativity. So we would expect that the chloromethane would be the most polar, whereas the iodomethane is the least polar, and that matches the dipole moments that we see here. Considering the molecules in the second row, one might expect acetone to be the most polar, given that it has the highest dipole moment. Unfortunately, it is not as simple as this, and most chemists would actually consider, of these molecules, water to be the most polar. So in addition to looking at the dipole moment, one must also consider the atoms which make up the particular molecule. And in particular, one's looking for a protic solvent. Now, a protic solvent means that you have a hydrogen attached to an electronegative element, such as oxygen or nitrogen. In other words, a hydrogen that is able to form hydrogen bonds. Such solvents are generally considered to be the most polar, even though they may not have the highest dipole moment. And this is because such solvents can stabilize a positive or negative charge which could exist throughout a reaction, for instance, the formation of a transition state. So water, alcohols, amines are all considered to be protic solvents, and all of these are considered to have a higher polarity than those solvents that, for instance, just contain halogens, or even, in fact, acetone. So, one is able to determine the polarity of a molecule based on looking at whether or not you have bond dipoles, looking at the molecular geometry, considering if you have a molecular dipole. So that's a reliable way. One can also look at the dipole moment. But in comparing different solvents or different molecules, it is also helpful to consider whether or not the solvent is protic. That is, if it has a hydrogen attached to an electronegative atom. In chemactivity 5, part 2, we'll now look at intermolecular forces. We will start with London dispersion forces and then ultimately look at dipole-dipole forces and hydrogen bonding. Our discussions here concerning polarity will assist us in examining these important intermolecular forces.